In another video, we talked about what Avogadro's number means. Avogadro's number is usually written as 6.022 times 10 to the 23. It's this very large number, and it defines a mole. Usually we write it without units, but you can write it as units as 1 over mole. So just like 12 is a dozen, this very large number is equal to 1 mole of stuff. So how do we get Avogadro's number? That's what this video is going to be about. And there's a very clever approach where we take pure silica of atomic weight 28 and we form it into a sphere. And what we measure with that is this. Avogadro's number will be equal to this quotient. It will be equal to lowercase n, where n is the number of atoms in the unit cell. So the number of atoms in a unit cell, and this would be a unit cell for silicon-28. And then it would be multiplied by the mass of this sphere that's been created. And we'll, in the experimental setup, they'll measure the volume very carefully. And so we would be able to get the density as mass per volume. And then we would also divide the whole thing by a cubed, where a is equal to the edge, the length of the edge of a unit cell. So unit cell edge length. Let's squeeze length in there. So if we have a cubic unit cell for silica-28, and we would because it forms in the cubic system, then this fellow here would have a total of 8 atoms. I'm showing over here the Lowry pattern for zinc sulfide because zinc sulfide, otherwise known as sphalerite, has the same kind of crystalline structure, the same arrangement of atoms as does silicon-28. So you can take a look at our video where we look at the unit cell case for zinc sulfide and just replace all the sulfur and zinc atoms with silicon-28 atoms, and you'd have the same kind of unit cell. There's 8 atoms, and we show how that's done in another video. So that's how we get this number here, which also comes out of X-ray diffraction. That would be something that would be derived. Both these diagrams, by the way, are from the online textbook by Dexter Perkins. So here he shows the Lowry diagram, and here he shows Bragg's law. Bragg's law has this lowercase n, which is not the same as this one. Here n is a whole number, which represents a value that relates, I'm going to write it a little bit differently here, the value of the wavelength to the angle at which X-rays impinge on a material. So if we have wavelengths of a given value, so the value from crest to crest, that would be our lambda. You could also go trough to trough, it doesn't matter. So that's the value for lambda here. That would be the wavelength of the incident light. What Bragg's law tells us is that that wavelength will scatter off some surface where we have these atoms of, in this case, silicon-28 here that are all lined up in a row. That energy, that X-ray energy, will scatter off in such a way that if we have other X-rays bouncing off other planes, then these waves here, the outgoing waves, will be in phase. They will constructively interfere. We will get constructive interference whenever n is equal to a whole number, like 1 or 2 or 3, etc. So when n is a whole number, if we take the sine of theta, so the sine of that angle there, multiply it by the d-spacing. This is the d-spacing here. It's the distance between these planes of atoms. Take that and again multiply it by 2, divide it by lambda, and if that quotient is equal to a whole number, then these fellows will interfere. Now, what does that mean? That means we'll get some bright spots, or perhaps in this case, some dark spots, depending on how we treat the image, that will represent where the energy is concentrated. It's the energy that is, the X-ray energy that is being transported through this crystal is going to get scattered. And how will it be scattered? We can use either Bragg's law, by thinking about it as reflected waves or other equations developed by Lowry, to look at scattered waves, and that'll tell us where this energy will be concentrated and where we won't get any energy at all, depending on whether the waves are interfering with one another constructively or destructively. But we have another video on Bragg's law to explain the rest of those details. The bottom line is that we can get this d-spacing. So what is the d-spacing? Well, take a look at these gray circles again. The way I've drawn these is a little bit inaccurate. We're showing here this line that goes through all those atoms, but those atoms are going to be touching. They'll have electron orbitals that are going to be much larger than the gray atoms. I'm not doing a very good job here, but we'll have the center of an atom there and the center of an atom there. And so the key thing is that the d-spacing is the distance between the center of those atoms. So d is essentially equal to 2 times the radius. It's equal to this radius plus that radius. So we have the radius of this atom plus the radius of that atom. So if we have atoms on the corners of this cube, then the d-spacing tells us the value for A, the edge of the length of the edge of the unit cell. So we know this guy. If we have a cube, we simply take that value of A, raise it to the 3rd power, then that will give us the total volume, multiply by density, and if we measure the mass and volume of this perfect sphere, or it's not really a perfect sphere, but near enough as we can create in the lab, then we know M, we know the density, and we know the volume. This is a pure number. This would be in grams. That would be in grams per cubic centimeters. This could be in cubic centimeters. All those units will cancel, and we'll be left with a pure number. What pure number do we get? We get 6.022, and then that's how we normally write it. We're not going to stop there. We're going to get 140,526 times 10 to the 23. And this is a value by Becker and colleagues that they derived in 2017. It's not the only value. There's a little bit of disagreement on these units here, but most people will get 022140, and then is it a 5 or is it an 8? So there's considerable error here. It's definitely non-zero, probably something that's at least 5 and maybe as large as 8. Anyway, if you wanted to use a more precise value for Avogadro's number, you could at least go out to this number of units and then, of course, multiply that by 10 to the 23, and that will give us, by definition, we just call that 1 mole. We just say it is because it just makes our life easier talking about a mole of atoms rather than a dozen atoms. A dozen atoms is not going to make up very much material, not anything large enough that we could see or hold or investigate very easily. So we'd much rather have a mole of zinc sulfide molecules or a mole of silicon-28 atoms before we start making any kinds of measurements. So that's how we get Avogadro's number today. There's also a very clever technique that Albert Einstein used where his equation could be used to get Avogadro's number without these very fancy and intricate experimental techniques to fashion a pure 10 kilogram sphere of silicon-28. And we'll try to take a look at that in another video.